Thank you for your kind introduction. Can you hear me? How about now? All right. So I'll be talking about phonon-mediated nuclear excitation transfer. For those of you who sat through the talk on yesterday, I'll be covering similar material but in more depth today. So we're interested in figuring out how excess heat works. I've been pursuing models for phonon-nuclear interaction, basically trying to understand the mechanisms for excess heat. Some years ago, I found a relativistic-based phonon-nuclear interaction, and I've been pursuing it. And this talk is basically focused on what's the interaction, what can you do with it, what are applications, and I'm going to be talking a little bit about interpretation of some experimental results that will be presented on Wednesday by Florian Metzler. In the relativistic problem for the quantum composite, you start with protons and nucleons, which constitute the nucleus. Normally you think of the nucleus as sort of like a rock or something that moves. You think about where it is and how fast it goes. You don't think about all the coordinates individually. And so to separate the internal coordinates from the center mass coordinates, that's what's involved in making a model for the quantum composite. And for the non-relativistic version of the problem, the separation is clean. For the relativistic version of the problem, it's not clean. There's a coupling between the center of mass momentum and the internal nuclear degrees of freedom. The basic idea can be thought of as this way. If you had two electrons interacting with one another in an atom, there's a magnetic interaction, and magnetic field is generated depending on how fast a charge is going. So if there's an electron in an atom, and if the atom moves, then the magnetic field generated by electrons going in the direction of the atom will be bigger. The ones going in the opposite direction will be smaller. So the magnetic force changes if the atom is moving. Well, the nuclear force works sort of similarly. The nuclear forces are momentum dependent. So if a nucleus moves, the nuclear forces change a small amount, but that provides a basis for coupling. So if your nucleus is moving back and forth, then the force changes, and whatever it is that causes the moving back and forth is going to be able to couple with the internal nuclear degrees of freedom. This effect was first noticed by Bright back in 1937. When he found it, he didn't like it, and he observed that if you're moving at constant velocity, you can rotate the interaction out. Subsequent authors agreed, and people haven't thought very much about it. But I'm of the opinion that this effect provides the basis for the anomalies that we've been looking at. If we have nuclei in condensed matter, we can model this particular interaction. If we use a finite basis approximation for the nuclear levels, we include this phonon-nuclear coupling term, and we add it to the other terms that normally show up in a condensed matter Hamiltonian, then we're in business. We can describe the interaction between condensed matter and nuclei consistent with this interaction. If we make a Born-Oppenheimer approximation, we can take the electrons out of the problem and replace them with the electronic energy. This is oftentimes done in condensed matter physics. If we quantize the vibrations into phonons and throw everything else out of the problem, we're left with a phonon-nuclear problem where we have vibrations, we have nuclear excited states, and we have interactions between them. And in a sense, this is the most basic problem that results from this kind of model. Okay, so excitation transfer. I've sort of talked about excitation transfer over the years. I've succeeded in put many a fine audience to sleep with my discussions. The way to think about it is that the phonon-nuclear coupling is a lot like the photon-nuclear coupling, at least algebraically. An excited nucleus can radiatively decay emitting a photon, and that's described by the photon-nuclear coupling, one photon created or destroyed, well, you can either promote or de-excite a nuclear state. Phonon business is the same way. You create or destroy one phonon, and you can go up or down for nuclear excitation. Now, the only thing is if you say, well, what's a one phonon emission? Can I have an excited nucleus and emit a phonon? The answer is, well, no. Your excited nucleus is probably tens of keV or MeV high, and your phonon modes are 50 millivolts or less. So one phonon processes, one phonon decay doesn't occur. So the question is there anything that happens you can actually see? And the answer is that you have to look for multi-phonon processes, and the lowest order one of interest is excitation transfer. So excitation transfer, over the years I'd like to do this thing with my fingers. This one's excited, this one's unexcited. Excitation transfer is going like bink. Anyway, that's how it works. It's a quantum mechanical thing. It goes through intermediate states that are off resonance. And I've been interested in this since the 1990s. So if there is a phonon-nuclear interaction, then there is going to be excitation transfer. We would expect it. The question is does it actually happen in real life? And I'll be getting to that. What I'm going to do is take a segue into an observation I made last week that I'm still thinking about. Over the years, I've been focusing on the E1, which is electric dipole transition matrix element. So the phonon-nuclear coupling is E1 for the nuclear part of the problem. So E1 transitions would be the lowest order transitions for this operator. And so what I found for the molecule case is that if I had a molecule with two tantalum-181 nuclei, which happens to have a low energy E1 transition, that I can analyze the indirect coupling coefficient, and I find out that there's destructive interference, that Mother Nature pops up and says, "Naha, you wanted to see this? Well, we'll see about that." The destructive interference makes it such that you don't get much coupling. And so I thought, let me try to do the crystal model and see if we get destructive interference through the crystal model. So I set up a crystal model for an E1 coupling, and it looks like this. For those of you who know quantum mechanics, it's obvious how this works. For the other ones, this is artwork that we can put on the wall or something. Anyway, the indirect coupling coefficient, you can calculate it out. And Mother Nature pops up and says, "Naha, you wanted to see that? Not this time." There's severe cancellation and destructive interference, and so it doesn't work. Now, recognizing this kind of effect, I introduced years ago the lossy spin boson model to make the system unbalanced to destroy this destructive interference. And I've been working with that for a long time, and predictions from that look good. People question, well, does nature actually work that way? Okay, so before the conference, I figured somebody would say, well, in your experiments, you're working with M1 transitions. Have you calculated excitation transfer for an M1 transition? And I was afraid I was going to have to say, well, no, I haven't done that yet, but I feel really bad doing that. So I took a day and a half and went through the calculations. The model looks like this. There's vibrations, there's nuclei, there's now 3 states, and you go from one state to a high state to a low state for an M1 transition. You can now calculate the excitation transfer, the resonant contribution. There's 96 terms. I was grinding away. The first one took me an hour. Second one took me half an hour. Third one about 15 minutes. You can see where this is going. Anyway, I started some terms together, and what do I find? Mother Nature didn't pop up this time. She sat down and said, "Okay, you can pass." There was no cancellation, and I was so flabbergasted by this. I went back and I checked the calculation twice and 3 times and 4 times and 5 times, and then I looked at the levels and I thought, oh, it's obvious that there shouldn't be any cancellation. The system's unbalanced. So this one's born unbalanced, and I've been kicking myself for having missed this over the last 20 years or so. Anyway, you don't have to do anything with these transitions to get them to show very interesting effects. Excitation transfer doesn't have cancellation. It's big, up conversion, down conversion. They're going to be big, cold fusion, excess heat. This is the way to do it. These are the transitions that do what you want. And all the unbalanced lossy spin boson model and calculation I've been doing are going to apply to this system, but without needing any loss. Here's low-lying E1 transitions in previous months and years, and even on the abstract. You can see I'm looking at the E1 transitions. Tantalum 181 is the lowest energy. And we went to some trouble to try to get a sample to work with to see excitation transfer. We didn't succeed. So we went to the M1, which is the one on the left-hand side, and mercury 201's the lowest energy example. I think is going to be a really important transition for us in the future. We chose to work with the iron 57, the famous Mossbauer transition at 14.4 keV. Okay, applications. So the first application that was apparent was one that came up in the late 1990s. People at that time were claiming to see low-level nuclear radiation. What's his name? Anyway, Pam Boss, Vysotskii, Lipson were all reporting low-level nuclear radiation. Vysotskii and Lipson were talking about energetic alpha particles over 10 MeV. That's not an easy thing to have come out of a lattice. And I was trying to think, well, how in the world could this happen? And an incoherent version of excitation transfer was the obvious candidate back in those days. So if you have D2 making a transition to helium-4, you've got about 24 MeV. If that gets transferred over to a palladium nucleus, then you can dig out an alpha particle or proton or neutron. You get lots of MeV kinetic energy in your particle coming out. That's sort of what's observed. But since it's incoherent, it would happen really slowly, which is also observed, namely the rates for the emission of these particles is really low. I remain interested in this problem, and I think one of these days we should do a systematic study of it. So the idea is that if it really works this way, you can predict what energy alpha particles, for example, come out for D2 going to helium-4 on the right-hand side. So you get many MeV, but depending on what you dig the alpha particle out of, you can figure out what the energy is going to be when it comes out. Similarly, if you have HD going to helium-3, you've got 5.5 MeV. So it's less energy, but depending on what you're pulling an alpha out of, it'll have less energy. But if you did a systematic study and matched the alpha energy against what was in the lattice, then you would be able to get some confidence that this is the mechanism that's going on. We're interested in pursuing this at MIT. Let me talk briefly about resonant excitation transfer. Okay, so resonant excitation transfer is excitation transfer where you don't exchange any energy with the lattice on average, that your initial state, this one, has the same energy as this one. And what resonant excitation transfer can do for you is it can make the nuclear phases be uniform. And if the nuclear phases are uniform, and if there's order in the local system, then you have the possibility of getting an angular anisotropy effect. And I was putting these slides together, and I was thinking, well, you guys know about our experiments, but it occurred to me that our experiments haven't been discussed, so I'm 2 steps ahead of myself. So we set up some experiments last year in the spring to try to see excitation transfer. And the basic idea was to start with, we wanted to start with an excited nucleus. So we were going to put in a radioactive source, put it on a plate. We looked around for several sources, and cobalt-57 turned out to be convenient because it fed into the excited states of iron-57. And iron-57 was had a relatively low energy nuclear transition at the 14.4 keV. So that's the one we were interested in. So we had, previous to that, we'd had a lot of failed experiments. First time we tried this excitation transfer experiment in May of last year, we saw an anomaly. And we were very excited about it. We were so excited we presented at a conference in Italy a few days later and babbled all kinds of crazy explanations for it. But subsequently, we've gained some understanding of what's going on and how it works, and Florian will talk about it in more detail on Wednesday. One of the experiments, in the experiments that have been done subsequently, on April 12th, I think we did this experiment. You can see the picture of the basic ideas. We have cobalt-57 on a steel plate. There's wood blocks, there's screws that got tightened. And basically, after the screws were tightened, it was put at a shallow angle to an Ortec high-purity germanium detector. And a spectra was taken and stored once per minute. And the time history you can see, and there's a straight line, a line that's almost straight that's black on top, which would be the decay corresponding to 271.74 day half-life. And what you see is the signal started out low and approaches that line. And that starting out low and approaching that line, in my opinion, is angular anisotropy. We're able to induce an angular anisotropy due to excitation transfer associated with the 136 keV line, which was a surprise and something that was unexpected going into this line of research. So the takeaway message from this is that there seems to be some evidence now in the laboratory for the existence of an excitation transfer process. Now, you might ask that the 136 keV state is very high energy. Lower energy transitions work better for excitation transfer. What about the 14.4 keV state? Do you see angular anisotropy on that? The answer is so far, no. So the question is, why not? And the why not is that the thought is that maybe the excitation transfer happens much faster on this transition. And if it happens faster, then other things would happen. One of the other things that appears to be happening in these experiments is delocalization. Again, I'm cutting into Florian's talk, and Florian will go into much more detail than me on this, but we've got in the evaporation of cobalt-57 on the steel, we get a ring. There's a hot spot where there's more cobalt-57. The cobalt-57, when it was made, didn't have much impurities in it, but when it decays, it makes iron-57. So the ring is mostly iron-57. And so when we focus on the hot spot, put a pinhole over it, and watch it with a SDD X-ray detector, silicon drift detector, X-ray detector, and we use a thermal pulse to apply pressure to the blocks, the wood blocks, we see a response here in the K-alpha. And the interpretation is that excitation is coming from elsewhere in the ring and in the circle to the hot spot, because that's where more iron-57 is. And we're seeing an increase in emission from the hot spot as a result of delocalization. So the excitation in this case is moving at least a few hundred microns, maybe a millimeter, maybe more than a millimeter. We need to do more work to figure out how far it's going. But the basic idea is that this notion of excitation transfer seems to maybe actually be happening in these experiments. One thing that's interesting is that for terahertz phonon exchange, so this favors high-frequency phonons, and few terahertz is the highest frequency phonons that are going to be in the residue. We would expect a single step of excitation transfer to be less than 100 angstroms, which means we're having an awful lot of excitation transfer steps to get us a few hundred microns here. Let me talk a little bit about the ratio of the K-alpha to the 14.4 keV gamma. So the nuclear physics of the level structure has been studied. It's one of the best studied transitions and decays known in nuclear physics. And you get when the beta decay of cobalt-57 happens, it happens by the cobalt nucleus eating a K-shell electron. So you tend to get a K-alpha some fraction of the time after that. And then subsequently, if you get a 14.4 keV excited nucleus, it can internal decay by internal conversion. So it can also give you a 14.4 keV or give you a K-shell hole. So you've got two ways to get a K-shell hole, which means that if you're doing an experiment, the ratio of the K-shell to the K-alpha to the 14.4 should be fixed in your experiment. You could maybe get some K-shell ionization, a small effect elsewhere. So what we see in the May 20th experiment, on the left is the K-alpha showing the non-exponential decay we got so excited about in the first place. And on the right's the 14.4, which we got so excited about. Basically, the anomaly's sort of similar for both of them. For one of them, it's 19% effect. For the other one, it's a 17% effect. So they're very close. In the August 10th experiment that Florian will actually explain, and I'm just interpreting the results from here. On the left is the K-alpha. On the right's the 14.4. And basically, the response of the K-alpha is much stronger in this experiment than the response of the 14.4. And if you like, that kind of thing shouldn't be happening. And I'm of the opinion that it's actually telling us something about excitation transfer. So in the limit that the excitation transfer is in the strong coupling limit, you've got these states with no excited nucleus, one excited nucleus, two excited nucleus, three, and so forth, all coupled with the phonon exchange, which are the diagonal blue lines happening. And if you injected one excited state into the system by the decay of 1 cobalt-57, then your energy is where the green line with the E on it is. Now, the one excited states, when it decays, it'll give you incrementally the right ratio of 14.4 to K-alpha. But if you have occupation of the zero excited, you don't get any decays from it, which would mean the total decay rate would go down. If you go to the two excited ends up having a new decay channel. And the new decay channel is one where one of the 14.4 kV states internally converts, and the other one internally converts. Each one costs on the order of 7.1 keV, and you have an energy E of 14.4. So you've opened up a new decay channel. It gives you 2 K-alphas. And that gives you a route to increase the K-alpha emission relative to the 14.4. If you go to 3 excited, 4 excited, there's no resonant decay modes open, which means your excited state can live longer, which means if you're busy excitation transferring from place to place to place, you've got longer than 98 nanoseconds half-life to do it. Higher order effects, if you have the excitation transfer and it's non-resonant, if you're exchanging phonons, if you do it again and again and again very fast, especially if you're in states that don't have open decay channels, then you have the possibility of doing it so much that you're going to accumulate a fair amount of off-resonant energy, which means that you have the possibility of up-converting and down-converting. I'm of the opinion that the Kornilova Vysotskii water jet experiment is an up-conversion thing. My friend Vysotskii violently disagrees with me on this, and we'll explain probably why later on. But the basic idea is that collimated X-rays are observed in this experiment and in some other experiments as well. I draw attention to a recent experiment by Ivlev, which I think is very important. For excess heat, the first thought was to try straight down conversion. The numbers didn't work. So a fancier approach is one that involves subdivision. Started out with a D2 to helium-4 transition. We got 24 MeV. Instead of trying to break that up into lots of phonons, we break it up into lots of excitations at lower energy, and then have these guys convert their vibrational energy to the lattice. This approach will work for HD going to helium-3, and D2 going to HT for tritium production in Tom Claytor's early palladium-D experiments. The model's consistent with phonon gain, phonon laser effects, the LETS 2 laser experiment. I think Mitchell Swartz's Raman experiments with the NANR are extremely important. I think in the Didick and Vysotskii experiments, the Compton scattering makes vibrations in the bulk. And those are my conclusions. Thank you.
Thank you very much.
Any questions and comments? Okay.
Can you, let's say, congratulations. Anyhow, can you explain more detail about your experiment setup? Because I'm not so clear. Maybe you use the steel and put the cobalt inside it?
We start out with a steel plate.
Yeah.
We evaporate cobalt in a hydrochloric acid solution, 10th molar, 50 microliters on the steel. It makes a ring. We take the steel, Florian takes 2 pieces of plywood, screws them down with bolts, and that's what was done for the May 10th experiment and also for the angular anisotropy experiment.
Okay, so the first thing, you saw the angular anisotropy, you said. But, but how come the anisotropy came? Because your source is completely isotropic.
Right. The source, so when the cobalt decays, it's an incoherent decay. The excited state, 136 and 14.4 kV states are produced incoherently. And so if you don't do anything, you get isotropic emission.
Yeah.
If you turn the screws down, you get stress in the metal plate. There's epoxy over the residue. So the steel and the epoxy sort of move a little bit differently.
So
the friction generates terahertz vibrations.
That means you put the different direction of stress, your angular anisotropy is changed to that direction.
Well, so the idea is that if we can produce some terahertz phonons that are non-thermal, that are either directional or anisotropic or non-equilibrium, then we have the possibility of getting resonant excitation transfer to occur. And if there's local order in the residue or in the steel underneath, there's some evidence that for that plate, the excitation transfer goes into the steel. When we look at it from the front and do a heat pulse, the emission goes down a little bit, which is evidence that the excitation is going into the steel and being absorbed. So we have excitation transfer that it makes phase coherence among the different nuclei, nuclear states. So instead of having just one excited state, we have many nuclei that have fractional occupation in phase. And when they radiate, it's not one nucleus that's radiating, it's many nuclei that are radiating, and the contributions from each interfere with one another. So in that experiment, the direction we were looking, there was destructive interference.
A short question.
A quick question. Since the phonons are bosons, they should be additive if you assume that the transition is not instantaneous, but over a period of number of oscillations. Are you not able to accumulate more energy in the phonon field? And that is in process of aligning the neighboring ones, the excited nuclei.
The picture is it's an M1 transition, 2 phonons at one place, 2 phonons at the other place. Go like this a few times and you're in business. You've got local, you don't have to go very far to get enough phase coherence to do this kind of thing.
Real quick question for you on this. Would you be better off with single crystal iron as opposed to steel so that you in fact have the possibility of more phasing going on?
Okay, so we originally were interested in iron generically because it had iron 57 in it, because we were trying to get iron 57 present. On the other hand, Kornilova and Vysotskii got some collimated emission with pieces of steel, and our piece of steel happens to be as near as we could get it exactly the same size as Kornilova's piece of steel. In retrospect, what we'd really like to have is a piece of iron 57 or iron 57 residue to do excitation transfer to.
Okay, thank you.
It's not that we're superstitious.
Shouldn't we expect that the ratio of coupling constants of your interaction to electron-phonon interaction be of the order of ratio of nuclear radius to Bohr radius? That is, what is the ratio of coupling constant to normal?
The nuclear radius is typically something like 3 Fermis or so, and the atomic
Exactly.
distances is multiple angstroms.
Exactly. So, what is the coupling constant in your case? What I'm saying is that the coupling constant should be extremely small.
Okay, so I have a formula for the coupling constant based on this theory. I have a poster for a calculation in the case of Talon 181.
What is the order of magnitude? That is, what enters in it?
Well, in the case of an A.CP matrix element, the A is on the order of 10 to the minus 6. For a single nucleus, the interaction energy is not very big. It's probably on the order of millivolt or tens of millivolt or something.
I see. Thank you.
Peter, you talk about two types of phonons, one the electronic phonon and two the nuclear phonon, I think. Is that right?
No, the phonons in this talk were all lattice phonons. They were
All lattice
vibrations.
phonons.
Yeah.
So when you're talking about the excitation and
I wasn't talking about nuclear,
Okay.
Okay, thank you.